If you enjoyed this podcast, please consider liking, sharing, and subscribing to the channel. Sharing it with your friends and family helps spread knowledge, and when we help others grow, we grow too. Thank you so much for listening. Let's dive into the podcast. Chapter 1: Foundations of a Silicon Giant, 1968 to 1971. Part 1: The Birth of Intel, Visionaries in Silicon Valley. Robert Noyce stared out his office window at Fairchild Semiconductor, watching engineers hurry between buildings in the California heat. It was 1968, and the man who had helped invent the integrated circuit felt trapped. Despite his success, corporate bureaucracy stifled his vision for the future of electronics. Down the hall, Gordon Moore shared similar frustrations. The two men had watched their innovations fuel Fairchild's growth. Yet they found themselves battling endless meetings and second-guessing from executives who didn't understand the technology they were trying to develop. Moore's famous observation about computer processing power doubling every 2 years had become gospel in Silicon Valley. But at Fairchild, his ideas moved at the speed of committee approval. The breaking point came during a particularly heated board meeting. Noyce proposed an aggressive new memory chip design that could revolutionize computing. The executives worried about costs and timelines. They wanted safer, incremental improvements. Noyce exchanged a knowing look with Moore. Both men realized they needed freedom to pursue their vision. That evening, they met at a quiet restaurant in Mountain View. The conversation started carefully, but soon they were sketching circuit designs on napkins and discussing what they really wanted to build. They dreamed of a company that could move fast, take risks, and push the boundaries of what semiconductors could do. The electronics industry was exploding, and they wanted to be at the center of that revolution. Finding investors proved surprisingly easy. Arthur Rock, a venture capitalist who understood the potential of Silicon Valley startups, listened to their pitch with growing excitement. When Noyce and Moore explained their plan to focus on semiconductor memory devices, Rock saw the opportunity immediately. Computers were getting smaller and faster, but they needed better memory systems to keep pace. Within months, they had secured $2.5 million in funding. On July 18, 1968, they officially founded Intel Corporation, a name that combined integrated electronics. They rented a small building in Mountain View, just minutes from their former employer. The early days tested everyone's resolve. They hired carefully, bringing in engineers who shared their appetite for innovation and speed. Andy Grove, a brilliant Hungarian immigrant with a reputation for demanding perfection, joined as their operations manager. His intense focus on discipline and results would prove essential as they tried to compete against established companies with much deeper resources. Their first products were memory chips that stored information more reliably than anything available. The technical challenges seemed impossible at times, but the team worked with an energy that surprised even themselves. They were building more than a company. They were creating a new way of thinking about technology. By 1971, Intel had established itself as a serious player in Silicon Valley's rapidly expanding semiconductor ecosystem. Their success attracted attention from computer manufacturers who needed better components for their increasingly sophisticated machines. The foundation was solid, and bigger breakthroughs waited just ahead. Part 2: Early innovations and market entry. Intel's first memory chips emerged from months of intense development in cramped laboratory spaces. The SRAM chips could store information faster than competitors, while their DRAM technology packed more data into smaller spaces. These weren't just incremental improvements. They represented fundamental advances in how silicon could handle information. The engineering team faced constant pressure to prove their designs worked reliably. Early prototypes failed repeatedly, forcing engineers to work through weekends, redesigning circuits and testing new approaches. Each failure taught valuable lessons about silicon behavior and manufacturing precision. The breakthrough came when they figured out how to make memory cells smaller while maintaining speed and accuracy. Computer manufacturers became their first customers. Drawn by the superior performance of Intel's chips, Companies like Burroughs and Honeywell needed faster memory for their systems, and Intel's products delivered what traditional suppliers couldn't match. Word spread quickly through the industry about these new chips that outperformed everything else available. Market reception exceeded expectations, but success brought new challenges. Competitors noticed Intel's growing reputation and began developing their own advanced memory technologies. Established companies like IBM and Texas Instruments had vastly superior manufacturing capabilities and distribution networks. Intel had to compete on innovation rather than scale. Strategic decisions during this period shaped the company's future direction. Rather than trying to match larger competitors on price, Intel focused on cutting-edge performance that commanded premium prices. They invested heavily in manufacturing quality, ensuring their chips worked consistently in demanding applications. This approach attracted customers who valued reliability over cost savings. The team learned valuable lessons about market dynamics and customer needs. Computer makers wanted partners who could deliver consistent quality and technical support, not just cheaper components. Intel's engineers spent time at customer facilities, understanding how their chips performed in real applications and gathering feedback for improvements. Manufacturing processes required constant refinement to maintain quality standards. The company developed strict testing procedures that caught defective chips before they reached customers. This attention to quality control became a defining characteristic that distinguished Intel from competitors who prioritized quantity over reliability. By 1970, Intel's memory chips had established the company as a credible player in the semiconductor market. Their reputation for innovation attracted talented engineers who wanted to work on advanced projects. The success of these early products generated revenue that funded research into even more ambitious technologies. The memory chip success provided crucial momentum for Intel's next phase of development. Engineers were already experimenting with more complex circuits that could process information rather than just store it. These early innovations had proven that Intel could compete with industry giants through superior technology and engineering excellence. The stage was set for even more revolutionary breakthroughs that would transform the entire computing industry. Part 3. The world's first commercial microprocessor, Intel 4004. While Intel's engineers were refining their memory chip technology in early 1970, an unexpected opportunity arrived that would change everything. A small Japanese calculator company called Busicom approached Intel with a complex problem. They needed custom chips for a new line of desktop calculators, but the traditional approach would require 12 separate specialized circuits. Ted Hoff, a brilliant engineer at Intel, saw something different in this challenge. Instead of creating 12 individual chips, he proposed a revolutionary idea: build one programmable chip that could handle multiple tasks by following different sets of instructions. This concept flew in the face of conventional thinking, where each chip served only one specific purpose. The project team faced enormous technical hurdles. They needed to squeeze an entire computer processor onto a silicon chip measuring just 1/8 of an inch square. The 4004, as they named it, would contain 2,300 transistors working together in perfect harmony. To put this in perspective, the room-sized computers of the era used far fewer transistors spread across massive circuit boards. Federico Fagin joined the project in April 1970, bringing crucial expertise in chip design. Working alongside Stan Mazer and Masatoshi Shima from Busicom, the team spent months solving problems that had never existed before. They created new ways to organize circuits, developed innovative manufacturing techniques, and established protocols for how instructions would flow through the processor. The breakthrough came when they successfully demonstrated that their tiny chip could perform calculations as effectively as much larger systems. The 4004 could execute 60,000 operations per second and address 4,096 bits of memory. These specifications might seem modest today, but in 1971, they represented a quantum leap forward. Intel initially planned to sell the 4004 exclusively to Busicom, but company leaders quickly realized they held something far more valuable. They negotiated to retain broader rights to the technology, paying Busicom $60,000 to modify their exclusive agreement. This decision proved prescient. The 4004 officially launched in November 1971, priced at $200 for a 4-chip set. Early advertisements proclaimed it as a computer on a chip, though few people grasped the full implications of this achievement. Engineers at other companies initially dismissed it as an interesting novelty with limited applications. The microprocessor's true significance became apparent as inventors and entrepreneurs began experimenting with its possibilities. Traffic lights, industrial controls, medical devices, and eventually personal computers all became feasible because of this single innovation. The 4004 had proven that computational power could be miniaturized and mass-produced. This breakthrough transformed Intel from a memory chip manufacturer into a microprocessor pioneer. The company's stock price reflected growing investor confidence in their technological leadership. More importantly, the 4004 established a new product category that would drive decades of innovation and growth, positioning Intel at the center of the coming digital revolution. Part 4. Going public and expanding horizons. By 1971, Intel faced a critical decision that would determine its future trajectory. The company had proven its technical prowess with groundbreaking memory chips and the revolutionary 4004 microprocessor, but ambitious expansion required significant capital. The founders recognized that private funding alone could not support their vision of transforming the computing industry. The timing for an initial public offering proved ideal. Wall Street had developed an appetite for technology stocks, particularly companies positioned at the forefront of the emerging electronics revolution. Intel's track record of innovation and growing market presence made it an attractive investment opportunity. Investors saw potential in a company that had already demonstrated the ability to create entirely new product categories. On October 13, 1971, Intel completed its IPO, offering shares to the public at $23.50 each. The stock opened strong, immediately validating the market's confidence in the company's future prospects. This successful debut raised approximately $6.8 million in initial capital, providing Intel with the financial foundation needed to pursue aggressive growth strategies. The influx of public investment capital transformed Intel's operational capabilities. Management allocated substantial portions of the new funds toward research and development, recognizing that sustained innovation would drive long-term success. The company expanded its engineering teams, recruited top talent from universities and competitors, and invested heavily in advanced manufacturing equipment. Going public also brought increased scrutiny and accountability. Intel now answered to shareholders who expected consistent growth and profitability. This pressure pushed the company to develop more disciplined business practices while maintaining its innovative edge. The leadership team had to balance short-term financial performance with long-term technological investments. The IPO proceeds enabled Intel to diversify beyond its initial focus on memory chips. While DRAM and SRAM products remained important revenue sources, the company began investing more heavily in microprocessor development. The success of the 4004 had demonstrated the enormous potential of programmable chips, and Intel positioned itself to dominate this emerging market. Manufacturing capacity became a crucial priority. The company used IPO funds to expand production facilities and improve manufacturing processes. This investment allowed Intel to meet growing demand while maintaining quality standards that differentiated its products from competitors. Scale became essential as the semiconductor industry evolved toward high-volume production. The public offering also enhanced Intel's credibility with customers and suppliers. Major corporations felt more confident partnering with a publicly traded company, viewing it as a sign of stability and long-term viability. This perception opened doors to larger contracts and strategic partnerships that had been difficult to secure as a private company. Intel's stock performance in the months following the IPO reflected growing investor enthusiasm for the semiconductor sector. The company's market valuation provided currency for potential acquisitions and attracted top engineering talent who received stock options as part of their compensation packages. The successful transition to public ownership marked Intel's evolution from a promising startup to an established technology leader. With substantial capital resources, expanded operations, and heightened market visibility, the company was positioned to capitalize on the accelerating demand for semiconductor innovation that would define the next decade of computing advancement. Chapter 2: The Rise to Dominance in Personal Computing, 1972 to 1991. Part 1: Breakthrough with x86 Architecture and IBM Partnership. Following Intel's early successes with the 4004 and 8080 processors, the company faced a critical moment in the late 1970s. The microprocessor market was heating up, and Intel needed something revolutionary to stay ahead. Their answer came in the form of the 8086 processor, a chip that would change everything. The 8086 represented a bold leap forward in processor design. Unlike its predecessors, this chip could handle 16 bits of data at once, doubling the processing power of 8-bit systems. More importantly, Intel built the 8086 with a clever architecture that could work with both 16-bit and 8-bit software. This backward compatibility meant companies wouldn't have to throw away their existing programs when they upgraded their computers. But having a great chip wasn't enough. Intel needed customers, and the biggest prize in the emerging personal computer market was IBM. The computer giant had dominated business machines for decades, but they were late to the personal computer game. By 1980, companies like Apple were capturing attention with their user-friendly machines, and IBM knew they had to act fast. When IBM decided to build their first personal computer, they broke their usual pattern of making everything in-house. Speed mattered more than control this time. They needed outside suppliers who could deliver quickly and reliably. Intel's 8088 processor, a slightly modified version of the 8086, caught their attention. It offered the power of 16-bit processing, but could work with cheaper 8-bit components that were readily available. The negotiations between Intel and IBM were intense, but crucial. IBM had strict requirements and demanding timelines. They wanted guaranteed supply, consistent quality, and competitive pricing. Intel, hungry for this massive opportunity, agreed to IBM's terms. They would provide not just processors, but also support chips and technical assistance. When IBM launched their personal computer in August 1981, it carried an Intel 8088 processor inside. The impact was immediate and profound. IBM's reputation for reliability and business credibility gave instant legitimacy to personal computers in corporate America. Companies that had been hesitant to adopt these new machines suddenly saw them as serious business tools. The partnership created a powerful feedback loop. As IBM's PC became the standard for business computing, other manufacturers rushed to create compatible machines. These IBM clones needed Intel processors to run the same software, creating enormous demand for Intel's chips. Software developers, seeing the growing market for Intel-based machines, wrote more programs for this architecture, making it even more attractive to computer buyers. This alliance transformed Intel from a component supplier serving engineers into a technology provider powering an entire industry. The x86 architecture became the foundation upon which the personal computer revolution was built. Every time someone bought an IBM PC or compatible machine, They were choosing Intel's vision of computing power. The success set the stage for Intel's complete transformation from memory company to microprocessor leader, fundamentally changing how the company would compete and grow. Part 2. The transition from memory to microprocessors. The partnership with IBM had transformed Intel into an industry powerhouse. But by the early 1980s, the company faced a crisis that would test everything it had built. Japanese manufacturers were flooding the memory chip market with cheaper, higher-quality products that undercut Intel's prices at every turn. Companies like NEC, Hitachi, and Toshiba had perfected manufacturing techniques that produced DRAM chips with fewer defects and lower costs than Intel could match. Andrew Grove, Intel's tough and methodical leader, watched as the company's memory business hemorrhaged money month after month. The Japanese competitors weren't just winning on price, they were delivering better products. Intel's engineers struggled to keep pace with the relentless improvements coming from overseas factories that operated with different cost structures and manufacturing philosophies. The situation reached a breaking point in 1984. Grove and co-founder Gordon Moore found themselves in Grove's office, staring at financial reports that painted a grim picture. The memory division that had once defined Intel was becoming a liability. Grove posed a question that would reshape the entire company. What would happen if we got kicked out and the board brought in a new CEO? What would he do? The answer came immediately. Any new leader would exit the memory business and focus entirely on microprocessors. This realization hit both men like a thunderbolt. They were discussing their company as if they were outsiders, yet the logic was undeniable. Intel's future lay not in the commodity memory chips that had made them famous, but in the complex microprocessors that powered personal computers. Making this shift required Grove to make one of the most difficult decisions in corporate history. Intel would abandon the business that had built the company and fire thousands of employees who worked in memory manufacturing. The human cost was enormous, but Grove understood that half measures would doom Intel entirely. The company needed to concentrate all its resources on microprocessors or risk losing everything. The transition wasn't just about closing factories and reassigning workers. Intel had to rebuild its entire identity around a different type of product. Memory chips were relatively simple components that competed primarily on price and reliability. Microprocessors were intricate devices that required constant innovation, software compatibility, and complex partnerships with computer makers. Grove's management style proved crucial during this transformation. Known for his direct communication and data-driven decisions, he pushed Intel's engineers to innovate faster than ever before. The company poured resources into developing more powerful processors, while Japanese competitors remained focused on memory products they were already dominating. This bold pivot positioned Intel perfectly for the personal computer boom that was about to explode across the world. By 1986, the company had completed its transformation from memory manufacturer to microprocessor specialist. The decision that had seemed so risky just 2 years earlier now appeared visionary. Intel had positioned itself at the center of a technology revolution that would define computing for decades to come. Part 3. Innovations in Processor Power and Architecture. The microprocessor revolution was just beginning, and Intel was ready to push computing power beyond anything the world had seen. In 1982, the company released the 80286 processor, a chip that would change how people thought about personal computers. The 286, as engineers called it, could handle 16 bits of data at once instead of the 8 bits that earlier processors managed. This meant computers could suddenly perform calculations twice as fast and work with much larger amounts of information. The 286 brought something revolutionary called protected mode, which allowed computers to run multiple programs at the same time without crashing. Before this innovation, running two programs simultaneously was like asking a juggler to handle flaming torches while riding a unicycle. It usually ended in disaster. Now, office workers could write documents while calculating spreadsheets, and computers became genuinely useful business tools instead of expensive toys. But Intel's engineers weren't satisfied with doubling performance. They wanted to create something that would make the 286 look slow. In 1985, they introduced the 80386, a processor that could handle 32 bits of data simultaneously. This quantum leap meant computers could access 4 billion different memory locations, enough space to run sophisticated software that had previously required expensive mainframe computers. The 386 changed everything about personal computing. Software developers suddenly had the power to create complex programs with rich graphics and advanced features. Video games became more realistic, business applications grew more sophisticated, and computers started appearing in places nobody had imagined. The chip's ability to run older programs alongside new ones meant businesses could upgrade without throwing away their existing software investments. Competition was heating up. Companies like Advanced Micro Devices and Cyrix were developing their own processors, trying to match Intel's performance while offering lower prices. Intel's engineers worked around the clock, knowing that losing technological leadership could mean losing the entire personal computer market they had helped create. In 1989, Intel answered its competitors with the 80486, a processor that integrated previously separate components onto a single chip. The 486 included a math coprocessor that had previously been sold separately, making complex calculations lightning fast. Clock speeds jumped to 25 MHz and higher, with some versions running at 50 MHz, speeds that seemed impossible just a few years earlier. Each new processor generation didn't just improve performance, it enabled entirely new categories of software. Desktop publishing programs turned ordinary computers into professional printing systems. Computer-aided design software allowed engineers to create detailed blueprints on screen. Multimedia applications began incorporating sound and video, transforming computers from text-based machines into rich, interactive experiences. The rapid succession of these processor improvements created a cycle that would define the computer industry for decades. Software developers pushed processors to their limits, creating programs that demanded more power. Intel's engineers responded with faster chips that enabled even more ambitious software. This technological dance accelerated innovation across the entire industry. By the end of the 1980s, Intel had established itself as the driving force behind personal computer evolution. The company's processors powered the majority of PCs worldwide, and each new generation brought capabilities that had seemed like science fiction just years before. The foundation was now set for Intel to become not just a component supplier, but a household name that consumers would actively seek out. Part 4. Building Brand Power, the Intel Inside Campaign. In 1991, Intel faced a growing problem. While their processors powered most personal computers, ordinary customers had no idea Intel existed. When people walked into computer stores, they asked for IBM, Compaq, or Dell machines. They never mentioned the chips inside those computers. This invisible presence troubled Intel's leadership, who watched competitors like AMD gain ground by offering cheaper alternatives to computer manufacturers. Dennis Carter, Intel's marketing director, proposed something radical for a technology company. Instead of selling only to computer makers, Intel would market directly to consumers. The idea seemed almost absurd at first. How do you convince regular people to care about a computer component they would never see or touch? Carter's team developed a simple but powerful concept. They would create a brand that consumers could recognize and trust, even if they didn't fully understand what a microprocessor did. The campaign needed to transform Intel from an anonymous supplier into a household name that people actively sought when buying computers. The Intel Inside logo emerged as the centerpiece of this strategy. The distinctive swirl design and memorable jingle would appear in computer advertisements, on store displays, and even on the computers themselves through small stickers. Intel offered computer manufacturers significant advertising rebates if they included the Intel Inside message in their marketing materials. The campaign launched with television commercials that avoided technical jargon. Instead of explaining processor speeds or architecture, the ads focused on a simple message: computers with Intel chips performed better and more reliably. The 5-note jingle became instantly recognizable, playing in electronic stores and computer commercials across the country. Computer manufacturers initially resisted the campaign. They worried that promoting Intel's brand would diminish their own product identity. Some companies feared that customers might switch brands based on the processor rather than the computer maker's reputation. Intel addressed these concerns by sharing advertising costs and proving that Intel Inside messaging actually increased computer sales. The results exceeded everyone's expectations. Within 2 years, brand recognition surveys showed that regular consumers could identify Intel by name and logo. More importantly, many customers began asking specifically for computers containing Intel processors. This consumer demand gave Intel tremendous leverage with computer manufacturers, who could no longer easily switch to competing chips without risking customer dissatisfaction. The campaign fundamentally changed how technology companies approached marketing. Intel proved that even invisible components could become consumer brands with the right strategy. Computer buyers developed emotional connections to Intel's products, viewing the company's processors as symbols of quality and innovation rather than mere technical components. By creating direct relationships with consumers, Intel protected itself from price competition and strengthened its position against rivals. The Intel Inside campaign transformed the company from a hidden supplier into one of the world's most recognized technology brands, setting the stage for Intel's continued dominance as personal computing expanded globally throughout the 1990s. Chapter 3: Cementing Leadership and Market Expansion, 1992 to 2005. Part 1: The Pentium Revolution and Computing Boom. In March 1993, Intel engineers gathered around banks of testing equipment in their Santa Clara labs, watching readouts that would change the computing world forever. The Pentium processor was about to break free from years of development challenges and technical hurdles that had pushed Intel's brightest minds to their limits. The chip represented a massive leap forward from Intel's previous 486 processors. Where the 486 handled one instruction at a time, the Pentium could process 2 instructions simultaneously through a revolutionary design called superscalar architecture. This wasn't just faster computing, it was fundamentally different computing. The processor also featured separate caches for instructions and data, allowing information to flow more efficiently through the chip circuits. Andy Grove, Intel's demanding CEO, had pushed his teams relentlessly during the Pentium's development. He understood that this processor would either cement Intel's dominance or allow competitors to catch up. The stakes couldn't have been higher, as personal computers were becoming essential tools for businesses and increasingly popular with home users. When Intel launched the Pentium in March 1993, they did something unprecedented in the chip industry. Instead of marketing the processor with technical specifications that only engineers understood, they created the famous Intel Inside campaign. Suddenly, consumers who bought computers started asking specifically for Pentium processors, turning a hidden component into a brand name. The timing proved perfect. Software developers were creating programs that demanded more processing power. Games like Doom pushed graphics capabilities to new limits. Multimedia applications required chips that could handle video, audio, and images simultaneously. The emerging internet needed processors capable of running multiple applications at once. The Pentium delivered on all these fronts. Manufacturing the Pentium presented enormous challenges. The chip contained over 3 million transistors, far more than any previous Intel processor. The company had to build new fabrication facilities and develop advanced manufacturing processes. Each chip required hundreds of precise steps, and even tiny imperfections could render the processor useless. However, in late 1994, Intel faced a crisis that tested the company's response to technical problems. Mathematicians discovered that the Pentium made small errors in certain complex calculations. While these errors affected only specific mathematical operations that most users would never encounter, the media coverage was intense. Grove initially dismissed the problem as insignificant, but customer anger grew rapidly. The situation forced Intel to make a costly decision. The company announced it would replace any Pentium processor for any customer who requested it. No questions asked. This response cost Intel nearly $500 million, but preserved customer trust and demonstrated the company's commitment to quality. The Pentium's success exceeded all expectations. Computer manufacturers built entire marketing campaigns around Pentium-powered machines. Performance improvements were immediately noticeable to users, making computers feel significantly faster and more responsive. The processor enabled new categories of software and helped drive the explosive growth of PC sales throughout the 1990s. By 1995, the Pentium had become synonymous with modern computing power, setting the stage for Intel's expansion into new markets and establishing the foundation for the company's next phase of growth. Part 2. Dominance in the server and workstation markets. With the Pentium establishing Intel as the driving force behind consumer computing, the company set its sights on bigger targets. The late 1990s brought explosive growth in business computing, as companies worldwide began recognizing that their operations depended entirely on digital infrastructure. This shift created an enormous opportunity that Intel was uniquely positioned to capture. The business world was changing rapidly. Internet commerce was taking off. Companies needed powerful servers to handle growing amounts of data, and workstations required processing power that far exceeded typical desktop needs. Intel's engineers recognized that serving these markets would require more than just faster versions of existing chips. They needed processors designed specifically for the demanding requirements of business-critical computing. In 1998, Intel launched the Xeon processor family, marking a decisive move into enterprise computing. These chips shared the fundamental architecture of Pentium processors, but incorporated crucial enhancements for business use. Xeon processors featured larger cache memory for handling complex calculations, support for multiple processors working together in the same system, and enhanced reliability features that businesses demanded for their mission-critical operations. The timing proved perfect. The Internet was transforming from an academic curiosity into the backbone of global commerce. Every website, every online transaction, every email server required powerful processors to handle the growing digital demands. Data centers were sprouting up across the world, each one packed with servers running Intel's Xeon chips. Intel's sales teams discovered that business customers operated very differently from consumers. While home users might upgrade their computers every few years, businesses made purchasing decisions based on long-term reliability, performance guarantees, and technical support. These customers were willing to pay premium prices for processors that could keep their operations running smoothly around the clock. Competition in the server market was fierce. Companies like Sun Microsystems, IBM, and others had established positions with their own specialized processors. However, Intel possessed a crucial advantage. Their experience in mass production and their relationship with major computer manufacturers gave them the ability to deliver Xeon processors at competitive prices while maintaining high-quality standards. The financial rewards were substantial. Server processors commanded significantly higher profit margins than consumer chips. A single Xeon processor could sell for several times the price of a desktop processor, and servers often required multiple processors working together. This created a lucrative revenue stream that would support Intel's growth for years to come. As the internet infrastructure expanded throughout the early 2000s, Intel found itself at the center of a digital revolution. Their processors were powering the servers that handled online banking, e-commerce sites, corporate databases, and the growing array of web services that businesses relied upon daily. This success in enterprise markets did more than generate profits. It positioned Intel as an essential partner for businesses worldwide and demonstrated the company's ability to adapt its technology for new challenges. The Xeon's dominance would soon face new tests as competitors recognized the value of these lucrative markets and prepared their own responses. Part 3. The Wintel Alliance and Strategic Battles. The Xeon's success in enterprise markets created the perfect foundation for Intel's most powerful strategic partnership. By the mid-1990s, Microsoft Windows had become the dominant operating system, while Intel processors powered the vast majority of personal computers. What emerged was more than just compatibility between two products. It became a mutually beneficial relationship that would reshape the entire technology industry. This partnership, known as the Wintel Alliance, created a powerful cycle of innovation and market control. Microsoft designed Windows to work best with Intel processors, while Intel optimized their chips to run Windows efficiently. When Microsoft released new versions of Windows with greater demands for processing power, Intel was ready with faster processors. When Intel developed new capabilities in their chips, Microsoft incorporated features into Windows that took advantage of these improvements. The business benefits were enormous for both companies. Computer manufacturers found it easier to build machines using this proven combination, rather than risk compatibility issues with alternative processors or operating systems. Consumers trusted the familiar pairing, knowing their software would work reliably. This created a barrier for competitors who struggled to break into a market dominated by this established partnership. However, this dominance attracted serious challenges from advanced micro devices. AMD had been producing processors since the 1970s, but gained significant momentum in the late 1990s with their Athlon processors. These chips offered comparable or sometimes superior performance to Intel's offerings at lower prices. AMD's K6 and later Athlon processors began winning market share, particularly among price-conscious consumers and gaming enthusiasts, who valued raw performance over brand recognition. The competition intensified as AMD introduced the Athlon 64 in 2003, which brought 64-bit computing to mainstream consumers before Intel's equivalent products. This technical achievement threatened Intel's reputation as the innovation leader and demonstrated that smaller competitors could still challenge industry giants with superior engineering. Intel responded aggressively to AMD's challenge through various strategies. The company increased research and development spending, accelerated product development cycles, and implemented competitive pricing in key markets. However, these business tactics eventually attracted scrutiny from regulators who questioned whether Intel was using unfair practices to maintain market dominance. Antitrust investigations began in multiple countries, with regulators examining Intel's relationships with computer manufacturers and their pricing strategies. The European Union launched a comprehensive investigation into Intel's business practices, while similar inquiries emerged in other major markets. These legal challenges created uncertainty and forced Intel to defend not just their technical capabilities, but their business methods. The regulatory pressure highlighted the risks of market dominance in the technology sector. While the Wintel alliance had created tremendous value for both companies, it also made them targets for antitrust enforcement. Intel faced the challenge of maintaining competitive advantages while operating under increased legal scrutiny. Despite these pressures, the partnership with Microsoft remained strong throughout this period. Both companies recognized that their mutual success depended on continued collaboration and innovation. As mobile computing began emerging as the next major technology trend, this alliance would face new tests in markets where different rules applied. Part 4. Embracing mobility and the wireless era. The technology industry had spent decades perfecting desktop computing, but by the early 2000s, a quiet revolution was beginning. People wanted computers they could carry. They wanted to work from coffee shops, travel with their machines, and stay connected wherever they went. Intel, masters of powerful desktop processors, suddenly faced a different challenge entirely. The problem seemed simple at first. Take existing processors and put them in laptops. But engineers quickly discovered that laptops demanded completely different priorities. Battery life mattered more than raw speed. Heat generation became critical when chips sat inches from users' hands. Weight restrictions meant every component had to shrink while maintaining performance. Sean Maloney, Intel's marketing chief, watched consumer behavior changing. Business travelers struggled with heavy laptops that died after 2 hours. Students wanted machines they could use between classes without hunting for power outlets. The wireless internet was spreading, but existing laptop technology couldn't take advantage of it effectively. Intel's engineering teams faced a puzzle their desktop expertise hadn't prepared them for. Creating efficient processors meant rethinking fundamental design principles. They developed new manufacturing techniques to reduce power consumption. They integrated wireless capabilities directly into their chip designs rather than relying on separate components. The breakthrough came with Centrino technology in 2003. Instead of selling just processors, Intel created complete platform solutions. Centrino combined efficient processors, wireless networking, and specialized chipsets into unified packages. Manufacturers could build thinner, lighter laptops with longer battery life and reliable wireless connections. Early adopters immediately noticed the difference. Laptops running Centrino technology stayed cool during extended use. Battery life stretched from 2 hours to 6 or more. Wireless connections remained stable as users moved between locations. Business presentations no longer required scrambling for power outlets or Ethernet cables. The market response validated Intel's mobile strategy. Laptop sales began outpacing desktop computers for the first time. Coffee shops installed wireless networks to attract customers with portable computers. Universities redesigned classrooms around wireless connectivity and student laptops. But success brought new competitors. Companies like ARM Holdings specialized in low-power processor designs. They understood mobile requirements from the beginning rather than adapting desktop technology. These firms attracted partnerships with emerging device manufacturers who prioritized efficiency over raw computing power. Intel realized they were entering unfamiliar territory. Desktop dominance didn't guarantee mobile success. Consumer priorities differed completely. Performance per watt mattered more than peak processing speed. Thermal management became as important as computational capability. The mobile transition represented more than technical adaptation. It signaled computing's evolution from stationary workstations to portable companions. Intel had built their reputation on delivering maximum performance for desktop applications. Now they needed to master the art of doing more with less power, less heat, and less space. As Centrino gained market acceptance, Intel engineers could see further transformations ahead. Mobile phones were becoming smarter. Wireless networks were expanding rapidly. Computing was becoming truly portable, creating opportunities and challenges that would reshape the entire technology landscape. Chapter 4: Challenges and Transformation in a Changing Industry, 2006 to 2020. Part 1: Multicore Processors and Slowing Moore's Law. By 2006, Intel faced a problem that would reshape everything. For decades, the company had thrived on Gordon Moore's famous prediction that transistors would double in density every 2 years. This relentless shrinking had made computers faster and faster. But now, the laws of physics were pushing back. The transistors had become so small that they were approaching atomic scales. Heat was becoming a massive issue. When processors got faster, they generated so much heat that cooling them became nearly impossible. Power consumption skyrocketed. Engineers watched in frustration as their latest designs required cooling systems that would drain laptop batteries in minutes. Something had to change, and Intel's answer was radical yet elegant. Instead of making single processors faster, they would put multiple processors on one chip. The Core 2 Duo, launched in 2006, marked this historic shift. 2 complete processing cores sat side by side on a single piece of silicon, sharing resources and dividing the workload. This wasn't just a technical change. It was a complete reimagining of how computers would work. For decades, software developers had written programs assuming they would run on one processor that kept getting faster. Now, they had to learn to split their programs into parts that could run simultaneously on different cores. This parallel thinking required entirely new programming approaches. Intel's engineers worked tirelessly to make this transition smooth. They designed sophisticated communication systems between cores. They developed new manufacturing techniques to pack multiple processors together efficiently. The cache memory system, which stores frequently used data, had to be completely redesigned to serve multiple cores without creating bottlenecks. The results were impressive. The Core 2 Duo delivered performance improvements while using less power than previous single-core designs. Laptops ran cooler and lasted longer on battery power. Desktop computers became capable of handling multiple demanding tasks simultaneously without slowing down. But this success came with new challenges. Software companies scrambled to rewrite their programs. Video games, photo editing software, and operating systems all needed updates to take advantage of multiple cores. Some applications adapted quickly, while others lagged behind for years. Meanwhile, the fundamental challenge remained. Moore's law wasn't dead, but it was definitely slowing down. Each new generation of chips required exponentially more investment and engineering effort. The easy gains from simply making transistors smaller were disappearing. Intel's response was to focus on architectural innovations beyond just adding more cores. They improved power efficiency, developed better prediction systems for what the processor would need to do next, and created specialized circuits for specific tasks. The era of raw speed improvements was giving way to an age of intelligent design. This transformation set the stage for even greater challenges ahead. As the mobile revolution began, Intel would discover that their desktop-focused expertise didn't automatically translate to the power-constrained world of smartphones and tablets. Part 2: Struggles in the mobile market and emerging competitors. Intel's engineers had mastered the desktop world, but the mobile revolution caught them completely off guard. When the first iPhone launched in 2007, it ran on an ARM-based processor that consumed a fraction of the power Intel's chips needed. This wasn't just a minor technical difference. It was a fundamental mismatch between Intel's strengths and what mobile devices required. The company's x86 processors were powerful but hungry for electricity. Smartphone makers needed chips that could run for hours on tiny batteries while staying cool in your pocket. Intel's processors, designed for plugged-in computers with fans, were like race cars trying to compete in a bicycle race. They had the horsepower, but not the efficiency. Intel tried to adapt. They created the Atom processor line specifically for mobile devices, shrinking their designs and reducing power consumption. But they were years behind competitors like Qualcomm, who had been building low-power chips from the ground up. ARM Holdings had licensed their processor designs to dozens of companies, creating an entire ecosystem of mobile chip makers. Intel faced not just one competitor, but an army of them. The numbers told a stark story. By 2012, billions of smartphones and tablets were shipping annually, almost all powered by non-Intel processors. Intel's market share in mobile remains stubbornly close to zero, despite massive investments. Company executives watched helplessly as the fastest-growing segment of the chip market slipped away. Making matters worse, advanced micro devices began its comeback. AMD had struggled for years, but under new leadership, they launched the Ryzen processor family in 2017. These chips matched Intel's performance while costing less and using innovative designs. For the first time in over a decade, Intel faced serious competition in their core PC and server markets. AMD's resurgence wasn't accidental. They had partnered with outside manufacturers instead of building their own factories, allowing them to access the latest manufacturing technology without massive capital investments. This strategy let them focus entirely on chip design, while Intel had to manage both design and manufacturing challenges simultaneously. Enterprise customers began seriously considering AMD processors for servers and data centers. Intel's profit margins, long protected by their near monopoly in high-end computing, came under pressure. Stock analysts questioned whether Intel could maintain its dominance across multiple fronts. The mobile failure wasn't just about lost revenue. It represented a strategic blindness that worried investors and employees alike. Intel had missed the biggest shift in computing since the personal computer revolution. Their engineering culture, so successful in the desktop era, had become a liability in the mobile world. As 2020 approached, Intel faced an uncomfortable reality. The industry they had dominated for decades was fragmenting. New players were succeeding with different approaches. The company that had defined the semiconductor industry now found itself fighting to stay relevant in a rapidly changing landscape. Part 3. Diversification into AI, IoT, and autonomous technologies. By 2015, Intel's executives could no longer ignore the warning signs. The mobile market defeat had sent shockwaves through the company, but it also served as a wake-up call. CEO Brian Krzanich and his leadership team realized they couldn't simply wait for the next computing wave to arrive. They needed to create it themselves. The strategy was bold but risky. Transform Intel from a PC-centric chip company into a diversified technology platform serving multiple emerging markets. The first major move came in 2015 when Intel announced its acquisition of Altera, a leading manufacturer of field-programmable gate arrays, for $16.7 billion. These specialized chips could be reprogrammed after manufacturing, making them perfect for applications that required flexibility and rapid adaptation. Altera wasn't just another acquisition. It represented Intel's recognition that the future wouldn't be dominated by general-purpose processors alone. Different applications would need different types of chips, and FPGAs offered the versatility to serve markets Intel had never touched before. Data centers began using them to accelerate specific workloads. Network infrastructure companies valued their ability to adapt quickly to new protocols. The artificial intelligence boom provided Intel's next big opportunity. Machine learning workloads didn't run efficiently on traditional CPUs, creating demand for specialized hardware. Intel launched its Xeon Phi processors and later developed dedicated AI chips, positioning itself against NVIDIA's growing dominance in this space. The company also acquired smaller AI-focused firms like Nirvana Systems and Habana Labs, building expertise in machine learning acceleration. Then came the move that would define Intel's diversification strategy, the $15.3 billion acquisition of Mobileye in 2017. This Israeli company had become a leader in autonomous vehicle technology, developing the computer vision systems that helped cars see and understand their environment. For Intel, it wasn't just about entering the automotive market. It was about positioning for a future where every vehicle would become a data center on wheels. Mobileye brought more than technology. It brought credibility in an entirely new industry. Automotive companies that had never worked with Intel suddenly saw the chip giant as a serious partner in the race toward self-driving vehicles. The acquisition also provided massive amounts of real-world driving data, a crucial asset for training AI systems. The Internet of Things became another frontier. Intel developed specialized processors for smart devices, from industrial sensors to home automation systems. These weren't high-margin products like desktop processors, but they represented scale. Billions of connected devices would need chips, and Intel wanted to supply them. Each acquisition and new product line created challenges Intel had never faced. Different markets meant different sales cycles, customer relationships, and competitive dynamics. The automotive industry operated on 5-year development cycles, completely different from the rapid pace of consumer electronics. AI customers demanded software support and developer tools, not just hardware. Critics questioned whether Intel was spreading itself too thin. The company was investing billions in markets where it had no established presence, competing against focused specialists who had years of head starts. But Intel's leadership believed diversification was essential for survival in an industry where single market dominance was becoming impossible. This transformation represented more than strategic pivoting. It showed Intel's determination to remain relevant as computing evolved beyond traditional boundaries, setting the stage for even bolder manufacturing investments ahead. Part 4. Manufacturing Renaissance, IDM 2.0 Strategy. By 2020, Intel faced a stark reality that shook the semiconductor industry. The company that once defined the cutting edge of chip manufacturing found itself trailing behind Taiwan Semiconductor Manufacturing Company, TSMC. For decades, Intel had maintained an unshakable advantage through its integrated device manufacturer model, designing and producing its own chips in its own factories. Now that same model seemed like a burden. Pat Gelsinger returned as CEO in February 2021 with a bold vision called IDM 2.0. This wasn't just another corporate strategy, but a fundamental reimagining of how Intel would compete. The plan combined Intel's traditional strength in manufacturing with the flexibility to work with external foundries when needed. More importantly, it included opening Intel's factories to outside customers for the first time in the company's history. The challenge was staggering. Modern semiconductor manufacturing required investments measured in tens of billions of dollars per facility. Each new generation of chips demanded smaller transistors, more precise equipment, and increasingly complex processes. Intel's 10-nanometer process had suffered years of delays, while TSMC raced ahead with superior 7-nanometer and 5-nanometer technologies. Customers like Apple had already jumped ship, moving their most advanced processors to TSMC. Gelsinger announced massive facility expansions across multiple states. New fabrication plants would rise in Arizona, Ohio, and other locations, each representing investments of $20 billion or more. These weren't just factories, but entire ecosystems requiring specialized suppliers, trained workers, and advanced research capabilities. The scale dwarfed previous industrial projects, rivaling the interstate highway system in ambition and complexity. The foundry business presented its own challenges. Intel had to convince potential customers that it could manufacture their designs without stealing their secrets or favoring its own products. Trust had to be built from scratch in an industry where intellectual property was everything. Companies like Qualcomm and NVIDIA, accustomed to working with TSMC's neutral foundry model, needed reassurance that Intel could separate its manufacturing and design businesses. Government support became crucial. The CHIPS Act provided billions in subsidies, recognizing that advanced semiconductor manufacturing was a national security priority. Intel positioned itself as the American answer to Asia's manufacturing dominance, promising to rebuild domestic production capabilities that had been steadily moving overseas for decades. The technical hurdles remained formidable. Each new process node required breakthrough innovations in material science, lithography, and process control. Intel's engineers worked on revolutionary techniques like extreme ultraviolet lithography and novel transistor architectures. Success wasn't guaranteed, and the competition wasn't standing still. This manufacturing renaissance represented Intel's biggest bet since its founding. The company was simultaneously trying to catch up technologically, build new business models, and restore America's position in global semiconductor production. The outcome would determine not just Intel's future, but the entire trajectory of the technology industry in the coming decades. Chapter 5: Reinvention and the Future of Computing, 2021 to Present. Part 1: Leadership Changes Amid Industry Turbulence. When Intel's board gathered in early 2021, they faced a stark reality. The company that once dominated the semiconductor world was bleeding market share to competitors. AMD had seized the performance crown, while Apple's move away from Intel processors sent shockwaves through the industry. Stock prices reflected investor anxiety, and employees wondered if their company could reclaim its former glory. The board's choice for a new leader surprised many observers. Pat Gelsinger wasn't just another external hire seeking to shake up corporate culture. He was coming home. 30 years earlier, Gelsinger had started his career at Intel as an engineer, rising through the ranks before leaving to lead VMware. Now, at 59, he was returning to the company where he had learned to build processors and manage complex technology teams. Gelsinger's arrival in February 2021 brought immediate energy to Intel's sprawling campuses. He spoke passionately about restoring American manufacturing leadership and recapturing Intel's position as the world's most advanced chipmaker. His background gave him credibility that previous leaders had lacked. Engineers respected his technical knowledge, while investors hoped his track record at VMware would translate into operational excellence. The new CEO wasted no time outlining his vision. Intel would invest massively in new manufacturing capacity, both in the United States and Europe. The company would also open its factories to outside customers, competing directly with Taiwan Semiconductor Manufacturing Company. This strategy, dubbed IDM 2.0, represented a fundamental shift in how Intel operated. Gelsinger's enthusiasm was infectious, but executing his ambitious plans proved challenging. Building new fabrication facilities required years of planning and billions in investment. Meanwhile, competitors continued gaining ground in key markets. Apple's M1 processors demonstrated that Intel no longer held a monopoly on high-performance chip design. Internal dynamics at Intel also complicated the transformation efforts. Decades of corporate culture don't change overnight. Some employees embraced Gelsinger's vision enthusiastically, while others remained skeptical about whether the company could truly compete with nimbler rivals. Engineering teams worked overtime to develop new architectures, but breakthrough innovations take time to materialize. The pressure intensified as quarterly earnings reports showed mixed results. Wall Street demanded quick improvements, but semiconductor development operates on multi-year cycles. Gelsinger found himself balancing investor expectations with the realities of rebuilding a technology giant. Then, in December 2024, shocking news rippled through the industry. Gelsinger was stepping down as CEO, effective immediately. The announcement caught many by surprise. Given his apparent commitment to Intel's long-term transformation, the board appointed interim leadership while beginning another search for permanent management. This sudden transition left Intel employees and industry observers questioning what had gone wrong. Had the turnaround efforts failed to meet expectations? Were there disagreements between Gelsinger and the board about strategic direction? The leadership change injected fresh uncertainty into Intel's already complex journey toward relevance in an increasingly competitive market. Part 2. Responding to AI and cloud computing demands. While Intel grappled with leadership uncertainty, the technology landscape around them was transforming at breakneck speed. Artificial intelligence had moved from research labs to mainstream applications, creating massive demand for specialized chips. Cloud computing services were expanding globally, requiring powerful processors that could handle complex workloads efficiently. Intel found itself at a crossroads, where traditional computing was giving way to AI-driven systems. The company's engineers had watched as competitors like NVIDIA dominated the AI chip market with graphics processors originally designed for gaming. These chips proved remarkably effective at the parallel processing tasks that AI systems required. Meanwhile, cloud service providers like Amazon, Google, and Microsoft were designing their own custom chips to optimize their data centers. Intel's traditional strength in general-purpose processors suddenly felt less relevant. Despite the management turmoil, Intel's technical teams pressed forward with ambitious projects. They accelerated development of their Gaudi AI accelerator chips, designed specifically for training and running AI models. These processors featured specialized architecture that could handle the mathematical operations AI systems demanded. The goal was clear: create chips that could compete directly with NVIDIA's dominant products, while offering better performance per dollar. Intel also expanded their Xeon processor line, with features tailored for cloud computing. These server chips included enhanced security capabilities, improved memory bandwidth, and optimized power efficiency. Cloud providers needed processors that could run multiple virtual machines simultaneously while keeping operating costs low. Intel's engineers worked to balance raw computing power with energy efficiency, knowing that electricity costs were a major concern for data center operators. The company formed strategic partnerships with major cloud providers and AI companies. These collaborations provided Intel with real-world feedback about what features mattered most in AI workloads. Software developers worked alongside hardware engineers to optimize code for Intel's new chip designs. The goal was creating a complete ecosystem where Intel processors would excel at AI tasks. Market research showed that AI chip demand would grow exponentially over the coming decade. Companies across industries were integrating AI into their products and services. Autonomous vehicles, medical diagnostics, financial trading systems, and countless other applications required powerful AI processing capabilities. Intel positioned itself to capture a significant share of this expanding market. However, the competition was fierce and well-established. NVIDIA had built strong relationships with AI researchers and companies. AMD was also developing competitive AI chips. Even tech giants like Apple and Google were designing custom processors for their specific needs. Intel faced the challenge of catching up while these competitors continued advancing their own technologies. The company's response required massive investment in research and development. New chip designs took years to develop and test. Intel committed billions of dollars to AI-focused projects while continuing to improve their traditional processor lines. Success would determine whether Intel could remain relevant in the next era of computing, where artificial intelligence would drive technological progress across every industry. Part 3. Renewed focus on manufacturing an open foundry model. Intel realized that manufacturing chips was more than just making products. It was the foundation of their future survival. While competitors built their businesses by designing chips and outsourcing production to Asian foundries, Intel decided to double down on something different. They would not only make their own processors, but open their factories to outside customers for the first time in decades. Pat Gelsinger announced the IDM 2.0 strategy, which meant Intel would operate as both a designer and manufacturer, while also serving as a contract producer for other companies. This represented a massive shift from Intel's traditional approach of keeping their advanced manufacturing capabilities exclusively for their own chips. The plan required building new fabrication plants across America and Europe, each costing tens of billions of dollars. The timing reflected growing concerns about chip supply chains. COVID-19 had exposed how dependent the world had become on a few Asian manufacturers. Governments suddenly realized that semiconductors powered everything from cars to smartphones to military equipment. When factories shut down in Taiwan or South Korea, entire industries ground to a halt thousands of miles away. Intel saw an opportunity in this chaos. American and European governments were offering massive subsidies to bring chip manufacturing back to their territories. The CHIPS Act in America promised over $50 billion in incentives. European leaders made similar commitments. Intel positioned itself to capture much of this funding by promising to build advanced factories that would reduce dependence on foreign suppliers. The company announced plans for megasites in Ohio, Arizona, and Ireland. Each location would house multiple fabrication plants capable of producing the most advanced processors. These weren't just factories. They were technological cities employing thousands of engineers and technicians. The Ohio facility alone represented a $20 billion investment that could expand to $100 billion over the following decade. Opening Foundry services meant Intel would manufacture chips designed by competitors and customers. This created awkward situations where Intel might produce processors that would compete directly with their own products. However, the revenue potential was enormous. Companies like Apple, NVIDIA, and AMD all needed advanced manufacturing capabilities that only a few facilities worldwide could provide. Intel's Foundry strategy targeted customers who wanted alternatives to Taiwan Semiconductor Manufacturing Company, which dominated contract chip production. Some companies worried about concentrating too much production in Taiwan, given geopolitical tensions with China. Intel offered manufacturing in more stable locations with strong government backing. The scale of investment required was staggering. Building a single advanced chip factory cost more than most companies' entire market value. Intel committed to spending over $100 billion on new facilities over the next decade. This bet assumed that demand for advanced chips would continue growing exponentially as artificial intelligence, electric vehicles, and 5G networks expanded globally. Success would transform Intel from a processor company into a manufacturing powerhouse serving the entire technology industry. This manufacturing renaissance represented Intel's boldest attempt to regain leadership in an industry they had helped create but no longer dominated. Part 4. Charting the course ahead: Innovation, Competition, and Impact. Intel stood at the threshold of a new era, its manufacturing bet already beginning to reshape the company's identity. The Foundry expansion marked more than just brick-and-mortar construction. It signaled Intel's return to its roots as an innovator willing to take extraordinary risks to secure the future of computing. Pat Gelsinger's vision extended far beyond traditional processors. His team worked feverishly on next-generation technologies that would power autonomous vehicles, smart cities, and quantum computers. The company's research labs buzzed with activity as engineers explored new materials and architectures that could push Moore's law past its apparent limits. These weren't incremental improvements, but fundamental reimagining of how chips could be designed and manufactured. The competitive landscape demanded nothing less than perfection. TSMC and Samsung maintained their manufacturing advantage, while NVIDIA dominated the AI chip market that Intel desperately wanted to reclaim. Chinese companies like SMIC represented emerging threats backed by substantial government investment. Intel faced the challenge of competing simultaneously against established leaders and rising challengers across multiple technology fronts. global supply chains added another layer of complexity. The COVID-19 pandemic had exposed the fragility of international semiconductor networks. Governments worldwide now viewed chip manufacturing as a national security priority. Intel found itself positioned as America's champion in the global technology race, carrying expectations that extended far beyond corporate profits to national competitiveness and strategic autonomy. The company's innovation pipeline promised exciting breakthroughs. Advanced packaging technologies could integrate different types of chips into single powerful modules. New memory architectures might eliminate traditional storage bottlenecks. Photonic computing offered pathways to dramatically faster data processing. Each potential breakthrough carried the promise of market disruption and the risk of massive investment with uncertain returns. Intel's workforce grappled with the scale of transformation required. Veteran engineers who had built careers on x86 processors now learned about AI accelerators and specialized computing architectures. The company recruited talent from universities and competitors, creating a melting pot of expertise that could either generate breakthrough innovations or struggle with cultural integration. The timeline for success remained unforgiving. Technology markets moved at breakneck speed, with new standards emerging every few years. Intel needed to execute flawlessly on manufacturing expansion while simultaneously developing competitive products for markets that didn't yet exist. The margin for error was virtually non-existent. As construction crews worked around the clock building new fabrication facilities, Intel's engineers raced to design the chips that would justify these massive investments. The company's future depended on proving that American innovation and manufacturing could compete with the best in the world. This chapter of Intel's story would determine whether the company could reclaim its position as the undisputed leader of the semiconductor industry or remain a respected but secondary player in the technologies shaping tomorrow's world.